Hello, my name is Kevin Nguyen, and this is my lab 5. So I chose the falling slinky. So introduction, so we're going to be observing the motion of a slinky when it's dropped from rest. Then I'm going to create a model of the motion from the stretched slinky dropped from the static equilibrium. So I'm going to do that in the code. And then we're going to analyze it using a computer generated model and compare if the slinky stays stationary like in the video. So the formulas that I'm going to be using is just the gravity, force of gravity, and then tension force. Then I'm going to use Newton's second law, so position and velocity to update each iteration of it. So this is my tracker. So I have I tracked A as the top of the slinky, and mass B will be the bottom of the slinky. And then this is what the coordinate system I set up. And the slinky I estimated by eyeballing his height to be around 6 feet. And then this would be probably around 5 feet. And so that'll be equal to 1.5 meters. And this is my tracker. So I'm going to play it. As you can tell, mass B is not moving at all at the bottom of the slinky, and only the top is moving. So once the top hits the bottom, both of them starts going down at the same time. And as you can tell, the plot is right here, the y-axis for the mass A and B. So until over here at 6 seconds, that's when the B started going down, and that's when A reached it. So for the code, so I first set up the ball, the trail, and the origin, and then the spring. And then you get the mass of the mass of the spring, which I googled to be 0.218 kilograms. Then the position is based off of my tracker position. And then delta T will be 0.001. And for my code, I'm only going to be using the top position since the bottom didn't really move. And then so G is for gravity, and then Ks is the spring constant of the slinky, which I googled also, is 0.84. And this is the length, which I estimated, which is 1.5. Then L was the position, L hat, and S would be the change. The whole time interval was 8.8 seconds, so you get the force of gravity and the spring. Add those two for the net force, and then you update the velocity and position. And then that's it. So this is for the model, since like I said, I only used the top and I coded it. So you can tell it's sort of linear. And this is my model over here. If I adjust, this is the ball is a slinky and just going down. Oops. And then so why did the bottom not move until the top of the slinky reached it? And this is because the bottom is by itself, having the tension force pulling it up and the gravitational force pulling it down, so it's equal. So the bottom stays the same until it gets information that the tension force changes, which is when the top of the slinky hits the bottom. So how to improve on this lab? I need a more accurate data placement on the tracker, which is human error. Have a better video quality to track my position of the slinky. I could also include air resistance and have actual experimental data of the exact slinky instead of Googling and educated guesses. And thank you. That's it.